No, I know Westvaco has it's a holiday for them. Usually companies that have unions. And so we were on section 9.3, and I went through it fairly quickly, so I did this in the other class as a kind of a further explanation of how you can use similar triangles to prove that the Pythagorean theorem is valid. So what we did was we took this outside triangle, which is this triangle, with sides A, B, and C, and this is what we're ultimately trying to prove, is that a squared plus b squared equals c squared. So you take the original triangle and draw a line from this vertex to the opposite side such that there's a 90-degree angle, and that creates two smaller right triangles. This right triangle, which is length B, H, and J, and the smallest triangle, which is here, which has side length H, A, and K. And they're similar because in this case, the larger triangle, we have these two angles, and it turns out these two angles are equal to each other. So anyway, you can prove that they are similar triangles because of the overlap of parts of the triangle. This is a right triangle, and this is a right triangle, right triangle. We just had to figure out which sides correspond to which sides. So if we were to do that, for example, these two sides would correspond because they're both the hypotenuse. And this is the longer side, so those two would correspond. And the shorter sides would correspond. So those are the ones I would compare between those two triangles. And then going from here to here, this would go to this one because they're both hypotenuses. These two would be the same because they're both the longer side. And then these two would be the shorter side, like that. And then you could go from the bigger triangles. You just have to figure out what the corresponding things are. And I was just checking. Oh, yeah, Harmony, I think you have your microphone on. If you can turn that off, turn talk off, because I heard some noise in the background. So what they were asking was, by proportion, they have this ratio. So the proportion is that C over B is equal to B over J. So we're going to use the left-hand side to be the large triangle. And so we see that side C is the hypotenuse, side B is the longer side. So if I compare these two, the hypotenuse is B, and the longer side is J. So I get C over B is equal to B over J. That's where that comes from. Comparing these two triangles, the fact they're similar, that means the ratio of side lengths is the same between corresponding sides. The second ratio they talked about was C over A, which is the hypotenuse to the short side. If we go down here, the hypotenuse to the short side is A over K. So the ratio of C over A, hypotenuse to short, is the same as A over K, hypotenuse to short. So that becomes A over K. So first case I compared these two, and the last case I compared those two. Then what you can do is you can take those ratios and do a cross multiplication. So if I cross multiply this ratio, I'll get that C times J is equal to B times B, or B squared. So this is just that rewritten. Likewise, this can be rewritten. So I'd have C times K is equal to A squared. And then you add these two together, and you can do that, as long as you're adding equalities together, you maintain the equality. So we get CJ plus CK is equal to A squared plus B squared. So it almost looks like the Pythagorean theorem. We have A squared plus B squared. If we factor out the C, we have a C multiplied each term here, so we can take it, factor it, and become C times J plus K. But if we go back to the original formula, K plus J equals C. So we can say since J plus K equals C, then we can rewrite this as C times C is equal to A squared plus B squared, or A squared plus B squared equals C squared. So there it is. That's the Pythagorean theorem. That's the proof using similar triangles. So the homework for this section, I don't know if I showed this last time or not. So we've gone through all the kinds of homework problems that you'll see. Describing different kinds of triangles. Actually, I think that was the second section. This is using the Pythagorean theorem as well as similar triangles. Our next test will be next Monday. So we are only going to go through section 9.5 as far as the material we're going to cover in the next test. So I'm going to say, yeah, review video. Pardon me? Yeah. Okay, so I'm going to open up the next section. So the next two sections are things that you should know well. We're just going to apply them to particular word problems. So I'm not going to give you time to write a lot of this stuff down. You can look it up in your book, the definitions. I'm not going to ask you to do the definitions. You may have to identify what the perimeter is, what the area is, but as far as memorizing definitions, you don't need to. So the perimeter of any polygon is the sum of the measures of the line segments that form its sides. Perimeter is measured in linear units. Because we're not going into things like trigonometry or even sines and cosines and tangents, the way you calculate the perimeter is just, they have to give you all the lengths and you just add the lengths together and you get an answer. The key thing I want you to get out of this is to remember to be consistent in units. So if the units for measuring the length of the sides is centimeters, the answer is in centimeters. If it's in meters, each part is in meters, the answer is in meters. And it's not just, it's meters, not meters squared or meters cubed. So perimeter is always linear units, which means feet, inches, centimeters, and meters. So here's some formulas that you've seen before, and all they are basically saying add all the lengths of all the sides of the polygon together. So with a triangle, you have three sides. You just add the three side lengths together. The only time that I could give you two lengths and you have to calculate the third length is if you had a right triangle, but otherwise we don't know enough to be able to calculate the third side given the other two sides. Therefore, you pretty much have to be given all the numbers you add together. So, and then we have a rectangle, which again is just adding the sides, the length to sides. The thing about a rectangle is two of the sides have the same value and the other two sides have the same value. So you can, I mean, ultimately, you're just adding L plus W plus L plus W. And depending upon how you group those together, you get a slightly different equation. So the perimeter can either be 2 times L plus 2 times W, because I have two of these sides, I have two of those sides, or you can factor out the two and just have 2 times the sum of the length and the width. So in this case, I could give you this length, and because it's a rectangle, you know this length and you know that length. So you have to kind of use a little bit of deductive reasoning, knowing that rectangles have sides, opposite sides with the same length. Okay, so that's pretty much for a perimeter. Perimeters of triangles, perimeters of rectangles. Piece of cake. Then we have what we call plane area. Plane area, not as like normal. It just means the area on a plane. So we're talking about flat surfaces. What is the area of a flat surface? And the flat surface could be a rectangle. It could be a triangle. It could be a circle, as long as they're flat, two-dimensional. That's what plane area is. And when you have something that's square or rectangular, you could probably kind of understand what area is, because it's a nice uniform square. So what I'm going to do here is I'm actually going to draw a few more lines. If I were to draw in the middle here and assume that each thing that I make is, oh, that didn't work. Let's try this again. Well, that's just going to do it again. So let me just draw some lines. I wanted to get little squares, not rectangles. So let's assume these are squares. So if I wanted to know the total area of the big rectangle, I would just add up the individual small rectangles. And let's assume that each one is 1 centimeter by 1 centimeter. And so the area of a 1 centimeter square, the area here, I'll call this A. A is just equal to 1 centimeter times 1 centimeter. It's just a little square. So I will get 1 times 1, which is 1, and I get 1 centimeter squared. So the area, the total area, is just all these little 1 centimeter blocks added together. So all I really have to do for a rectangle would be to count the number of blocks. So I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 that way, and 1, 2, 3, 4, 5. So I could say there are 50 1 centimeter squared blocks. Therefore, the total area is 50 square centimeters. So depending upon what unit system you work in, there's kind of like a standard block size you could come up with. If you were dealing with meters, you could have 1 by 1 meter block. If you were dealing with inches, you could have 1 by 1 inch block. And each one of those is going to be 1 square unit. So what happens if you have something? Well, for a rectangle, instead of counting all these blocks up, it's just simpler to take the width and multiply by the length, and that'll give you the total area. And the width and length don't have to be whole numbers. They can be decimals. So let's just make up a problem. So let's say we have a rectangle that has this dimension of, say, 10 centimeters. And this dimension is 6.6 centimeters. So to find the area of this rectangle, we just take the length, which is 10 centimeters, and we multiply it by the width, which is not an integer, but that's okay, 6.6 centimeters. And you multiply the numbers together, you get 66, and the units are centimeters squared. So anytime we have an area calculation, you need to be careful to include the proper units. So you have to see what the original object is measured in, and whatever that is, and they have to be in the same units. We don't want one in meters and one in centimeters, or one in the other way around. So we're consistent with our units, and then you just do the math and you get centimeters squared. So if I could put 66 blocks inside here. It's not going to come out to be nice even blocks, because I'm going to have fractions of blocks in the y direction. Okay, so that's for a rectangle. So you've got some really easy problems here in the book. Find the perimeter in the area of this rectangle. So the perimeter is just equal to 2 times the length. And make sure we include units. And the length doesn't have to be shorter than the width in this case, but it is in this case. But I mean, the width is shorter than the length, but it doesn't matter. Okay, so that's these two distances, and then we have 2 times the other distance, which is 2 centimeters. So we get 5 centimeters. 2.5 times 2 is 5, and then we get 2 times 2 is 4. So the answer is 9 centimeters. If we were to drive around the edge of this, we had a little speedometer or a odometer. If we drove around the edges, we would have a total of 9 centimeters. 2.5 plus 2 is 4.5. 4.5 plus 2.5 is 7. 7 plus 2 is 9. So that's what that is. And the area of a rectangle is just the product of the two dimensions. So the area is just equal to 2½ centimeters times 2 centimeters, which is 5 centimeters squared. So it's area, so we have to make sure it's centimeters squared. Okay, a square is just a rectangle with the two sides equal to each other. So for a rectangle, the area was the length times the width, but because they're the same, since S and L and W are the same, you just multiply the two together and you just get S squared. Okay, moving onward. Okay, this one's more interesting. Those are the ones you should know by now. Now, if you have a parallelogram, so the parallelogram is shown by the blue figure, and it says that the area of the parallelogram is equal to the length of the base, which in this case is from here to here, times the height. Not the length of this side here, but the height, which is the distance from the base to the opposite side. So they're showing the height to be this distance. But, you know, the height is anything. It's always the distance between the two parallel sides. Well, two of the same parallel sides. So that doesn't change no matter where I draw this thing. And again, because we are not talking about trig functions, they have to give you both of these to calculate. Well, yeah, because you might be given this and that, but you've got to know this a little bit to be able to calculate it using the Pythagorean theorem, so they'd have to give you some more information. Usually they just give you the height and they give you the base and you just multiply them together and you get the answer. And the reason it is that way is you can think of this. I have a triangle here. Actually, what do I have? Actually, what you do is the way you can think about how they get this is if you took this little triangle, which is outside of the existing triangle, and that area here, let me just draw this. Oops. Because of symmetry, what I can do is I can take that triangle and then I can take this and then I'm going to rotate it like that, and I'm going to stick it right in there, and now it becomes a rectangle. So it's a rectangle, and this other part's straight. So what I do is I borrow some from one side and I stick it in the other. So what I did is I took this and copied it and moved it over here, and now it becomes a rectangle which has a base of B and a height of that. So that's how you get the formula. So again, here's a problem. It's just a simple, trivial calculation. And actually, we cannot calculate the perimeter. So we can only calculate the area for this problem. They don't give you enough information to figure out what the length of this side is. So the area of a parallelogram is the base times the height. In this case, the base is 4 inches. The height is 2 inches. Therefore, the answer is 8 inches squared. Okay. Most people get this right because they can multiply 2 times 4. They just forget to keep the units in the correct, not only consistent units, but the appropriate exponent. Now, a trapezoid has a similar kind of thing, except you take the average of the two bases, and then you multiply that by the height. So it's b, small b, which is the length of the shorter parallel side plus the length of the other parallel side. And multiplying it by the height. It's still going to be units of squared because I've got b and b are both in units, are length units. So length plus length is length, and then length times length is length squared. So the correct units. Now, how would you do this one? Well, what you do is you kind of you would take, you'd like go halfway up here, and you'd make a little rectangle like that, and then you would group those together, and then you would rotate it around, and you would stick it up there. So that would create that side, and then you do the same thing on the other side. You go halfway up this thing, you draw a triangle, and you group those together, and you rotate it 180 degrees, and you stick it up there. And so what I did is I stole this part and I moved it up there, and I stole that part and I moved it up there. And the length from here to here is the average of these two. So this length from here to here would be b, small b plus big B divided by 2, and the same down here, and then you have the height of the rectangle. So again, you take your trapezoid and you do a little bit of conversion, you change it into a rectangle, which we can easily determine what that is. So again, we can't find the perimeter of the trapezoid because we don't know what the length of these sides are. But we can calculate the area using the formula. It's 1/2 the height, which is 3 centimeters, times the sum of the other two sides, 4 centimeters plus 5 centimeters. So the total area of the trapezoid is going to be 1/2 times 3 times 9. 3 times 9 is 27. So we get 27 in the numerator, 2 in the denominator, and the units are, again, because it's area, they have to be the squared of the original units. And then finally, the area of a triangle. So the area of a triangle is 1/2 the base times the height. And when you have a triangle that's like this one, which is a acute triangle, you can always draw your height from this side to that side. So it's always, this height is always inside the triangle. And then you also notice we've created a right triangle here. Now let me create a duplicate of the triangle. Okay, making lots of copies of it. So that's the original orientation. If I take this and rotate it around to there, and the third way I'd do it would be, I guess, this side right now. So these are all the same triangle, just oriented differently. So the base is going to be a different dimension depending upon how I rotate it. This is the base for this triangle. This is the base for this triangle. So the hypotenuse is the base. The shorter side is the base. The longer side here. So this is going. These three B's are going to be different values. And then you're going to have the height. And the height in this case is exactly what we had up here. It's the distance from this corner to the opposite one with a 90-degree angle. Here the height would be that distance, and over here the height would be that distance. And again, all the heights are going to be different depending upon the orientation. But all of those are going to give you the same answer. This height times that base times a half gives you an area, which is exactly the value you would get by taking this base times that height times a half, and likewise here, this base times that height. So as long as you use the definition of what is the base is completely up to you. Usually the base is the horizontal side, but I can take the same triangle and make every side be the horizontal side, and I'm going to get a different value for the base, and I'm going to get a different value for the height. But no matter which way this thing's oriented, I'm going to get the same area because it's the same triangle. Otherwise the formula would be useless. Now if you have an obtuse triangle, what will happen is the height, which is the distance from the base to the opposite corner, in this case it's outside the triangle. So what you do is you extend the base, and then where the opposite corner intersects the extended base, that's your height. Because you might think, oh, well, this is the height. But that's not what you do. You go from the opposite side to the line that corresponds to the base. So let's try it. I haven't tried this before, so let me try this. I'm going to take this one and just see how, in the other orientations, it might actually be inside the triangle. I think it will be. So, you know, in this case, the height is outside. It's over here. But if I took that and I cloned it, I'll clone it twice, and we'll add a page. So here's, take this one, move it over there. So I'm going to rotate this thing around. So this is the horizontal side, and then I'm going to take this one over there. Oops. So do that. And what's the other option? I guess it's this one right there. So for this case, the base is this side, again, the horizontal side, and the height would be this. So one of the orientations actually gives you the height inside. Whereas 2 out of the 3 apparently give you the height being outside the triangle. So they extend that. And that's apparently not horizontal, so I'm going to have to rotate it a little bit more. So there it is. So then the height for this particular case, this would be the base, and the height would be this distance. Actually, I think that's just the same triangle, but oriented the other way. I think actually there's a third orientation, which would be, which way would it be? It would be that way. Okay, yeah. So actually 2 out of the 3, no, that one still would be over there. Okay. Yeah, I think 2 out of the 3 would have the height outside of the box. Anyway, the thing I wanted to point out was, you know, even though it looks like these things are very different, because they're triangles, they're still going to add up to the same area. They're going to still result in the same area. So here's a simple case. You've got a triangle. I don't really care what kind of triangle it is. I've got the base, I've got the height, so it's a simple matter of calculating it. 1/2 the base times the height what the other side lengths are, I don't really care, because all I'm doing is calculating the area. So I'll take 0.5 times 22 times 38, and I get 0.5 times 22 times 38. I get 418 millimeters squared. So hopefully you don't find those difficult. And then you have some word problems that you have to do. So these are where you actually are going to try to draw what they're talking about, and then use that information to come up with some kind of algebraic equation that we're going to solve. So it's kind of using geometry to calculate or to create algebraic equations. So what we have is a stained glass window in a church that is in the shape of a square. So we're going to draw a square. And so the sides of a square are just S. And it says that the perimeter of the square is 7 times the length of a side in meters. So the perimeter is equal to 7 times the length of a side. Which seems kind of weird to me, because you would think the perimeter is 4 times the length of the side. Oh, decreased by 12. Okay, decreased by 12. Okay, now it makes more sense. Otherwise, that wouldn't make any sense at all. So the perimeter is 7 times the length of the side in meters, decreased by 12. So that's the perimeter. And it says find the length of the side of, oh, what else do we know here? The length of the side of the window. Okay, so this is from just the problem description. But we also know the perimeter has to be 4 times the length of each side. And it's saying that, and these are both the same thing. One's the perimeter as described by this cryptic description, and one is just from the definition of what is the perimeter for a square. So by doing that, we get 2 equations. Oops. So now we can just set them equal to each other. They're the same value. One is specified in the problem, one is from the definition of the perimeter. And so we'll get 7s minus 4s is equal to 12. What I've done is I've subtracted 4s from both sides. I've added 12 to both sides. Then I can combine like terms. And then I can divide by 3. So I get the side has to be equal to 4. And if I plug 4 in, I'll get 4 times 7, which is 28, minus 12, which is 16, and 4 times 4 is 16, so I get the same answer. So I've double-checked my answer by plugging it back into the original equations. Okay, problem 28. A wall pendant in the shape of an isosceles triangle is in the shape of an isosceles triangle. Each of the 2 equal sides measures 18 inches more than the third side, and the perimeter of the triangle is 54 inches. What are the lengths of the sides of the pendant? So any of these problems where you're not given a drawing, it's probably good to draw something. So I'm going to draw an isosceles triangle. And I think that is an isosceles triangle. Here we go. And I don't know whether this is bigger than those or which way it goes. I have no idea, so I'm just going to have to guess. It's just an isosceles triangle. So what it says is that each of the 2 equal sides, which are these two have the same, is 18 inches more than the third side. So I'm going to call the third side x, and this side is going to be x plus 18. And because it's an isosceles triangle, the other side has to be x plus 18. So that sounds pretty good. 2 equal sides. The 2 equal sides are 18 more than the third side, which I'm calling x. What are the lengths of the sides of the perimeter, given the perimeter is 54? So the perimeter of a triangle is just equal to the sum of the three sides of the triangle. So I take these two, the long sides plus the short side. I combine like terms, so I've got 3 x's, 1, 2, 3, and 18 plus 18 is 36. So subtract 36 from both sides. 54 minus 36 is 18. I'm remaining with 3x on the right-hand side, divide both sides by 3. So I get x is equal to 6. And so this side is going to be 24, this side's 24, and this side is 6. Same kind of deal here. Instead of doing it in terms of words, they give you the lengths. So we create, this is problem 42, the perimeter is 42. The perimeter is also the sum of the 3 sides of the triangle. So we have an algebraic equation. Again, we have 3 x's, so we'll combine those together into 3x. Then we have 2 plus 7, which is 9. Then we're going to subtract 9 from both sides. So 43 minus 9 is 33. 42 minus 9 is 33. Divide both sides by 3. Solve for x. You get x is 11. So this side is 11, this side is 13, and this side is 18. So I just take the value of x that I've determined and plug it back in to the original triangle. I'm going to show you one thing about solving. We do algebra next semester, kind of a review. I'm going to, so this is the pre-review. So if I wanted to, instead of subtracting 9 from both sides, another way of thinking about solving algebraic equations is that anytime you take a quantity and you move it from one side to the other, so instead of subtracting, I'm moving things. So what I would do is I would say, well, if I move the 9 from this side to the other side, it becomes negative. So this goes over there, and as a consequence, it becomes negative. And then 42 minus 9 is 33, and then I do it the same way. And you may think, well, what's the difference? Well, there are cases where thinking about moving something instead of subtracting it, what it does is it eliminates this extra line of stuff. So let's look at another case. So if you had 4x plus 5 is equal to 2x minus 7. So instead of subtracting 2x from both sides or adding 7 to both sides or something, subtracting 5 from both sides, what I'd say is, well, you know, algebra says I need to move all the constants to one side and all the other stuff, the variables, to the other side. So what I would do is I'd say, okay, I'm going to move everything, to all the x stuff, to the left side. So when I move 2x to the left side, it becomes negative 2x. On the right-hand side, I have negative 7, and when I move negative 5 to the other side, 5 to the other side, it becomes negative 5. So then I can combine these two. 4 minus 2 is 2, and negative 7 minus 5 is negative 12. And then I can divide both sides by 2, and I'll get negative 6. So I'm going to give you another example, which we did in physics today. And when you get to physics or chemistry, a lot of times the equations are just variables. You don't have a lot of numbers. You just got everything is a variable. And you want to solve for something that's, you're given all the information except one variable, and you need to solve for that. So let's say I wanted to solve for T, which turns out it's a tension in a rope. To solve for T, I'd say, well, solve means I need this by itself. So I could say, well, I'm going to add W sub x to both sides, but the easier way to do it is say, if I want to move this to the other side to isolate T, I would take this and I would just change the sign. So negative W sub x becomes positive W sub x. And then I have my solution. I've got it solved. M is the mass, A is the acceleration, and W sub x has to do with the weight of the object. And then when you have problems like this, where you're dealing with a lot of variables, it's just cleaner to think about, instead of subtracting it from both sides, to think about moving it from one side to the other. I'm going to give you another example here. X plus 7 minus 3 is equal to 3x minus 8. Okay, so how would I do this? What I would do is I say, okay, all the variable stuff, get over on the left-hand side. So this one's already on the left-hand side. This one, I would change the sign and move it over there. And then the constants, I would move the 7, so that would become negative, and the negative 3 would become positive. And then I can combine like terms, so I get negative 2x is equal to negative 13, or negative 12. So I don't know if anybody teaches you that way, but so you get x is negative 6. So little word for the wise. Okay. So you got some more of these things where you have to use, this is, you're given the area, so you just have to identify the appropriate equation. The area of a trapezoid is 1/2 the base, or the height, times the sum of the two bases. So all we do is plug it in, 30. There's no units on it. So 30 is the left-hand side. You have 1/2 the height. The height is 3. The small length base is x. The big B base is x plus 4. And then you just have to solve for x. So let's see what happens. We'll use what we just learned here now. So we're going to have 1/2 times 3 is 3/2. And combining these two terms, you're going to have 2x plus 4. So what I'm going to do first, actually, I could multiply this by the whole term. I could multiply this by 2 and this by 4, but when you can avoid fractions, it's a good thing. So just to do something different here is I'm going to multiply by the reciprocal of the term here. So what I'll get is 30 times 2/3 is equal to 2x plus 4. So when you multiply 2/3 times 3/2, the 2's cancel out, the 3's cancel out, and therefore I don't have a fraction on my fraction on my x term, which makes life easier. Here I can simplify it. 30 divided by 3 is 10. So I get 20 is equal to 2x plus 4. I'm going to move the 4 to the other side, so it'll become negative. Then I'm going to do the math. 20 minus 4 is 16. And then I divide both sides by 2. And I get x is equal to 8. So the answers are 8 and 12. And if I take this plus that, which is 20, divide by 2, which would be 5. 5 times 3 is 15. Well, did I do something wrong there? Did I leave something out? Let's see, 8 plus, that's 20. 20 divided by 2 is 10. 10 times 3 is 30. Okay, so that does work out. Okay, and then we have a circle. The circumference of a circle is just the distance around the circle. And remember, we have the diameter, which is the line segment from one side of the circle to the other side, going through the center of the circle. And then we have the radius, which is going from the center of the circle to the circle. And we know that the diameter is twice the radius. So the circumference is either pi, 3.14159, times the diameter, or 2 pi times the radius. Again, you should have seen that many times. And the area of a circle is pi times the radius squared. They don't show it here, but it also could be equal to pi times the diameter squared divided by 4. So that's the other. If you have diameter, usually people make, I do it the same thing. You work these circle problems and you forget which one you're given. You're given the radius and you think it's the diameter. You get the diameter, you think it's the radius, and you don't pay attention enough. And I've done it. So that's usually where people mess up when it comes to calculating the area or the circumference of a circle. Make sure you read the problem and see what it says. Don't assume it's the radius. Just check out what it says. Just seeing where we are in this whole thing. Okay, yeah. So, again, you're given some dimension of the circle, either the diameter or the radius, and they ask you to calculate the other 3 things. So in this case, we're given the diameter. So I'm going to say D is equal to 4 meters. The radius is the diameter divided by 2. So that's 4 meters divided by 2, which is 2 meters. The area, or the circumference, is just 2 pi times r, or pi times d. So we get 2 pi times the radius, which is 4 pi. If I don't tell you to multiply it out, you just leave the pi as a number. You don't write it out as a decimal form. Likewise with the area. The area is pi r squared, so you get pi times the radius, which is 2 meters squared. That'll give you 4 pi meters squared. Again, the units are the length squared. The circumference, which is the perimeter of a circle, is meters, just like others are meters. The only time this works out where the circumference and the value of the circumference and the value of the area is the same is when the radius is 2. So don't always expect that to happen. It's just the case where 2 squared is equal to 2 times 2. But if you had 3, 3 squared is not equal to 3 times 2. Here they give you the area, and they want you to calculate the circumference, the diameter, and the radius. So let's write it out. The area is pi r squared, which is equal to 50 pi centimeters squared. So this is the equation for the area in terms of the radius. This is the actual value. So what we want to do is solve for r. We can't go from area directly to circumference. You've got to calculate the radius first, and then you can go back and calculate the circumference. So what we're going to do is we're going to take our original equality, and we're going to divide both sides by pi. So that means pi over pi is 1, so we get r squared is equal to, again, pi over pi is 1, so we get 50 centimeters squared, and so the radius is the square root of 50 times the square root of centimeters squared. Well, the square root of anything squared is just the original thing, so what we get is the square root of 50 centimeters. And the radius is in centimeters. It's a length. So once you have the radius, then you can calculate the diameter. The diameter is twice the radius. So you'll get 2 times the square root of 50 times centimeters. And the circumference is just 2 pi r. So r is down here, so you get 2 pi times the radius, which is the square root of 50 centimeters. So we get 2 pi, I get the same thing, there's not much you can do with it. So that's the circumference. So the key thing is if you're given area, you've got to calculate radius. Once you have radius, you can calculate the other things. If you're given the circumference, you have to calculate radius, and then you can calculate the other things. So it's always, if you're given radius or diameter, you can calculate everything from that, but when you have either area or circumference given, you have to calculate the radius first and then go back and get the other stuff. So this is one of these algebra problems. In this case, they tell you to use pi as 3.14, which is an approximation. This is problem 51. It says, with the given area, calculate x. What is the x is 4 times the diameter. So what we would do is we'd say the diameter is 4x, because it's showing the entire distance. Therefore, the radius is 2x. Radius is half the diameter. The area of a circle is equal to pi r squared. So we're given the area. We're asked to calculate the radius. So we would take the area divided by the approximation for pi. And if we do that, we'll get, they pick the area, so this number is reasonable, is 9. And so r is equal to, and actually something's wrong here. What am I doing wrong? 3. Oh, they're asked to find the value of x. Okay, yeah. So r is equal to 3, which is the square root of 9. And r is equal to 2x. So going back and figuring out what x is r divided by 2, which is 3 divided by 2, which is 1.5. So that's how you get to the final solution. So it's just a matter of using the definition of the area with the given value of x, creating an equation, and solving for r, which then allows you to solve for x. Or we could have put it in terms of x, I guess. That's probably what they were looking for. Before you gather the facts. So there you go. That's my political comment to today. It's not really political. It's a. What's that? I think that was the CIA. Well, I don't know. Hoover was. Yeah, no, he was the FBI. He was FBI. Okay. So if you see me with some woman that's not my wife, don't call her up and tell her it's no. Snitching, yeah. Okay. Number 56. Carpet cleaner charges $80 to shampoo an area of 31 feet by 31 feet. What would be the charge for an area of 93 feet by 93 feet? So there's two ways of looking at this. You can think of it as a proportion problem, or you can think of it as a cost per unit area. We're going to look at both of them, because this is actually something you might actually use, figure it out. If you're buying tile, you can buy 100 square feet of tile for such. You have 500 square feet of floor space. How much is it going to cost me? So in terms of they're charging on an area basis. So what we would do is we could set up a ratio. $80 is to 31 feet by 31 feet, which is going to give me an area. It's a rectangular. They don't say it, but it's a rectangular area. Or actually, it's a square area. And so we're going to set up a proportion, and we want to know how much are we going to charge for 93 feet by 93 feet. So that is doing it as a proportion. Now, just like I showed you here with moving stuff around instead of subtracting stuff, you know, I said a way of doing algebra is to say I'm going to move this to the other side and make it negative. There's a similar kind of philosophy you can use for solving ratios. And the rule is that when you have a pure ratio like this, if you have something in the denominator on one side, you can move it to the numerator on the other side, as long as you're multiplying. So what I'm trying to do is solve for x. I want x by itself. Well, it's not by itself because of this stuff, the denominator. So what I can do is I can say, well, I'm just going to move this from the denominator on the right-hand side to the numerator on the left-hand side. So rather than cross-multiplying and dividing all this stuff and getting all confused, all you have to do is multiply this side by the denominator. So when I'm multiplying, it means I'm moving it to the numerator. So I get 93 feet times 93 feet. In one nice simple move, I've solved it, and then I can just, you can see the units cancel out. So all I have to do is multiply the numbers together. So you get $80 times 93 times 93 divided by 31 divided by 31, and I get $720. And you can see I have dollars here, so that's the final answer is dollars. So that is the amount it would cost me to do a rug this size. So that's using proportions. The other way would be cost per square foot. How do you do that? Well, you take the cost, $80, and divide by the square footage, 31 feet times 31 feet. So you'd have 80 divided by 31 times 31, and you get the cost per square foot of being 0.0832 blah, 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 blah. Okay? And this is dollars per square foot. So then to calculate the higher area, I would say, well, my new area, or my if I use this area, I'd get $80, but my new area is just 93 feet times 93 feet. It's a rectangle, or it's a square, so I just multiply those two together, and I get that my new area that I want to calculate it is 8,649 square feet. So my cost is going to be my cost per square foot times my square footage. So I got my cost per square foot by using my initial information. So that's 0.0832 dollars per square foot times 8,649 feet squared, and I should get the same answer if I did it right. $719.59. Okay. It's not exactly the same, and that's because I rounded this off to 3 decimal points. But you see, you get the same answer. This one seems a lot easier to me. By rewriting the problem as a proportion, and then you don't, when you put it into your calculator, you don't have any round-off errors. Only way I could not have round-off errors is by going out to however many digits my calculator, and I'd still probably be off by something or other. So, okay, the final things in this section are finding the areas of complicated shapes. And like most things that are complicated, to solve complicated problems, you have to break it down into smaller, less complicated problems. If you look at anything, any task, it seems daunting to start with, but if you break it down into steps, bite-sized steps, then you're in good shape. So what we have is, in this case, it's pretty straightforward. We have a triangle, a rectangle, and a parallelogram. And the question is, what is the total area of the combined figure? So all we have to do is make sure we have all the dimensions of each part and then apply the appropriate equations. So in this case, the total area is the area of the triangle plus the area of the rectangle plus the area of the parallelogram. Well, the area of a triangle is 1/2 the base times the height. The area of a rectangle is the length times the width. And the area of a parallelogram is equal to the length times the height. Or the base times the height, I guess is what they said. So we just have to identify what these parts are. So for our triangle, this is the base. The height is 9 centimeters, or 9 units. So the area of the triangle is going to be 45. The area of the rectangle is just it's just the length times the width. So that's going to be, the length is 10, the width is 4. And then for the parallelogram, these are both 10 units, and the height is 3, so that's 10 times 3. And you just plug all that in there, and you get a number. So we're going to have 0.5 times 10 times 9 plus 10 times 4 plus 10 times 3. Get a total of 115. So that's the total area. So that's pretty straightforward. That's problem number 60 in your book. Now here's a little more complicated one. What we have is a rectangle and 2 semicircles. So it looks like a hockey rink, sort of like a hockey rink. We see that this dimension is 3, so that's the radius of the semicircle. The other one's 3. These are right angles. So here's my rectangle. Here's my semicircle. I've got 2 semicircles, so I could just find the area of the circle, or I could find the area of 2 semicircles. Gives you the same answer. So in this case, the total area is the area of the rectangle, which is the length times the width, plus 2 times the area of the semicircle. Well, the area of a circle is pi times r squared. So the area of a semicircle would be pi times r squared divided by 2. You see those cancel out. So we get either 2 semicircles or 1 circle. And then we just plug the numbers in. So the length is 8. The width of the rectangle is 6. So I almost wrote 3 down, but you got to make sure that you're identifying the correct dimension. So the radius is 3, but this distance is 6. And then we have pi times the radius, which is 3 squared. And to that point, we have, because we're mixing pi with no pi, we have to do that in decimal form. So 6 times 8 plus pi times 3 squared. And we get the total area is 76.3 units. Rounded off to 1 decimal point. Okay. So those adding stuff together. Now, what we have here is we have the shaded area. And so again, what we're going to do, instead of, the hard way would be to say, I've got a trapezoid here, I've got another trapezoid there, I've got a rectangle there, and I've got a triangle. So I could have two trapezoids, a rectangle, and a triangle. But the easier way of doing it would be to say I've got a rectangle and I've got a triangle, and the net area is going to be the rectangle minus the triangle, instead of trying to make it up into more complicated shapes. You always want to make it made up of the simplest shapes that you can. And sometimes using subtraction is easier than using addition. So what I'm going to do here, I'm going to say the shaded area is going to be equal to the area of the rectangle plus the area of well, there's two triangles. We'll call this triangle 1 and we'll call this triangle 2. So we're going to take the area of triangle 2 and we're going to subtract the area of triangle 1. Instead of, like I said, you can make a trapezoid, a rectangle, and a triangle. So that's too complicated. So we got to make sure we have all the dimensions we need. Well, for the rectangle, we have 28 by 24, so we're good there. For this longer triangle, we have this. Well, this is the height. So since this is 90 degrees, this is the height. And we need this distance right there. So we need to figure out what that distance is based on the other given information. So what we would do is we'd say, well, from here to here is 28 centimeters using this information. So that's 28 centimeters. If this triangle makes up 19 centimeters of it, then this little bit right here is 9 centimeters. 9 plus 19 is 28. And therefore, this base of this triangle here is going to be 38, which is the total distance minus 9. So this distance is equal to 29 centimeters. So I had to use a little bit of math to get the actual base of that triangle. So let's just plug the numbers in. So the area of the big rectangle is 28 centimeters times 24 centimeters. The area of this triangle is going to be 1/2 the base, which is this distance, 29 centimeters, times the height, which is 24 centimeters. And then I'm going to subtract the area of the small triangle, which is 1/2 the base, which is 19, times the height, which is given as 16. And then we just do the math. So we'll do that and quit. So we get 28 times 24, the area of the rectangle, plus the area of the triangle that's shaded in, and then we're going to subtract the area of the white triangle, which is what we're taking out of it, 0.5 times 19 times 16. And so the total area is 868 centimeters squared. So we're almost done. We'll finish this up on Wednesday, then we'll move on to section 5, which is talking about volumes and surface areas of three-dimensional bodies, like cones and spheres and circular cylinders and stuff like that. So let me go ahead and actually give you the assignment for this. There we go. So there's the homework assignment for section 4. As you can see by the number of problems, they're not that long. Each problem is not that long.
Oh, is this the one that he's going to give us
Oops, sorry. So this is due next Monday as well. Now the next one I'll assign, there'll be one problem probably about volume, and so you can turn it in after the test, but you'll have to know how to do it, so you might do it ahead of time anyway. Also, let me take a roll here before I forget. Make sure I didn't miss anybody. Okay, let's see. Actually, I need to. Yeah, hold on just a second. I'm gonna put it back up. I just need to make it so I can minimize this thing. Okay, let's see what I got here. Let's see anybody else who came in. It's low Monday here. Nobody's coming to class. What's going on here? I saw Timber online and some others. We'll see who else snuck in online. Justin's here. I'll let you get by with it. Okay. Morgan, let's see who we got left here. Melissa, Morgan, Kinsey. Melissa, Morgan, Kinsey, Morgan. Okay, let's see who else. There were other people that I'll get here. Timber.
Did you see my homework?
Yeah, I got Timber ready. Yeah, I'll check out these other people.
Did you see my homework on your chair?
What's that?
Oh, okay. Just checking.
Yeah, I did. Yep. I've got your old.
Okay.
I've got your whole
By the
old
way, my
homework here
twin
too.
said hi.
Okay. Okay. How's it going? Hello.
See ya later.
Okie dokie. Let's see who else I got here. Megan was there. Caitlin. Who else? Okay. Caitlin. And Megan. And who else? Somebody else. I didn't see Katie. Yep. Stop the recording.